Basic principles of IR spectroscopy. IR spectroscopy works on the principle that when a sample is irradiated with a light of particular frequency, some of the energy from the light will be absorbed by the molecule and it causes the molecule to vibrate. So now the frequency of the light that will be absorbed will depend on the type of bonds that is present in the molecule and will actually indicate the functional group that is present in the molecule. So basically with IR spectroscopy, we can find the functional groups. Normally, at room temperature, all organic molecules are said to be in motion, which involves vibrational modes such as stretching and bending. Let's take an example of a diatomic molecule. Here we are taking HCl. This bond right here, this covalent bond right here, cannot be considered as a rigid stick. Instead, they are going to behave more like a vibrating spring, right? So therefore, the type of vibration that exists in this molecule is stretching vibration. Now, when you take molecules that contain 3 or more atoms, it's going to be complex and it's going to include both stretching and as well as bending vibrations. And each one of these, we will have the symmetric and asymmetric stretching. Symmetric and asymmetric. And under the bending vibrations, we also have the in plane and out of plane. So these two right here, scissoring and rocking, comes under the in plane bending vibrations, and twisting and wagging comes under the out of plane bending vibrations. While the stretch is a vibration that occurs along the line of the bond, which basically is going to increase the length of the bond. So whenever a stretch happens, the bond length increases. Okay, a bending vibration normally is going to change the bond angle of the molecule. Okay, so this changes bond angle. It doesn't increase the bond length, instead it changes the bond angle. So this is the basic difference between the stretching and bending. And normally it takes more energies to stretch the bond than to bend the bond. So the energy that is required, or the frequency that is required to stretch the bond, is going to be more, whereas the energy that is required to bend the bond will be less. Infrared radiation has just the right range of frequencies, that is 4,000 to 600 centimeter inverse, to correspond to the frequencies of the stretching and bending vibrations of bonds in organic molecules. Now, the instrument that is used to obtain the IR spectrum is called as the IR spectrophotometer. In an IR spectrophotometer, the sample is irradiated with frequencies of IR radiation, and the frequencies that pass through the sample, basically those frequencies that are not absorbed by the sample, is now detected by the detector. And then a plot is constructed between percentage transmittance and wave number. When you say 100% transmission, all of the energy of the radiation is going to pass through the molecule. But lower values of percentage transmission is going to indicate that some of the energy is being absorbed by the molecule. And these downward spikes in the IR spectrum is what we call as absorption bands. So these are called as absorption bands. All of these downward spikes are called as absorption bands. The absorption bands are characteristic of a particular bond in the molecule, and therefore it's possible for us to determine the functional group that is present in the molecules. Let's now take a look in this compound. This compound has got two functional groups. We do have a carbonyl function group, and then we also have an hydroxy group. This hydroxy group normally absorbs at a wave number of 3,400, and you can see that there is an absorption peak around this region. Okay, and the carbonyl group in a ketone is going to absorb around 1,700, and obviously you can see an absorption band there. So when you have a compound for which the functional group is not known, what you will do is you will take the IR spectrum of the compound and find what absorption bands are present, like find the frequencies of the absorption bands and match them with the bonds that it would correspond to. There is a newer type of IR spectrophotometer called as the Fourier transform IR spectrometer. Fourier transform IR spectrophotometer. Now this has got several advantages over the conventional IR spectrophotometers because it's highly sensitive. And one of the reasons why it's highly sensitive is because instead of scanning through the frequencies sequentially, it measures all frequency all at the same time. And also it utilizes a mathematical operation called as the Fourier transform, to determine the frequencies which pass through the sample. Let us now find out how the sample is prepared for the IR spectrophotometer, for the use in IR spectrophotometer. So this would be sample preparation. For sample preparation, we can use two things. One is we can use the salt plate. So this disc right here that you're seeing is basically salt plate, which is made of sodium chloride. These plates are generally more expensive and are transparent to IR radiation. So let's say that your compound is a liquid. So what you will do is you'll merely put a drop of liquid and then that is sandwiched between these two salt plates and then put it in the slot that is available in the IR spectrophotometer for it to be analyzed. For solid samples, we have to use a solvent that is transparent to IR radiation. So you basically need to dissolve the solid sample in the solvent, and then that dissolved solution should be applied as a tiny spot in between the two salt plates and has to be analyzed. You can also use the KBR pellet method. So this method right here is KBR pellet method, in which case the sample needs to be mixed with the powdered KBR and it will be pressed into thin transparent film, which is called as the KBR pellet. Okay, and then it will be put inside the slot and then it will be analyzed in the IR spectrophotometer. IR spectrum. The IR spectrum is divided into two different regions. One is the functional group region and the other one is the fingerprint region. The functional group region is between 4000 to 1400 centimeter inverse and the fingerprint region is between 1400 to 600 centimeter inverse. So this one right here is the functional group region where most of the functional group is going to show up. This one right here is the fingerprint region. Just as the name says, the fingerprint region is going to be characteristic of the compound. Even if the two compounds are going to have exactly the same functional group, their fingerprint region is going to be definitely different. They're not going to be identical because the functional groups are in two different environments. Also, it is important to remember that most of the stretching vibrations occur in the functional group region because it takes more energy to stretch a bond than to bend a bond. While the stretching vibrations occurs between 4000 to 1400 centimeter inverse, the bending vibrations occurs between 1400 to 600 centimeter inverse. So here we will see the bending vibrations and here we will see the stretching vibrations. So it's always going to take more energy to stretch a bond than to bend a bond. So we normally focus more on the stretching vibrations than the bending vibrations for identifying the molecule. And remember, the IR cannot identify the molecule completely. All we can get from the IR is the functional group. Here is a table containing the frequencies of some important IR stretching vibrations, and it's very important that you know the approximate values for these frequencies corresponding to the different types of bonds. When you look into the IR spectrum, there are bands that vary in their intensity. So the nature of the bands that are obtained in an IR spectrum would definitely be useful in identifying the functional group in the molecule. So now let's take a look into this IR spectrum. You can see that there are some bands which go all the way to the bottom, and there are some bands which are lying in the middle of the spectrum, and there are some bands which are actually on the top of the spectrum close to the 100% transmittance. Now these bonds that lie close to the bottom of the IR spectrum are called as intense bonds, strongly intense bonds. So they are going to have strong intensity. These bands right here which are lying in the middle are said to have medium intensity. And these ones which are on the top are said to be weak. Also there are some bands which are broad. Say for example, the OH peak produces a very broad signal, and that is because of hydrogen bonding. We'll talk about that later. But there are also some absorption bands which are very sharp. Say for example, this peak right here, this absorption band right here is sharp. So the nature of the absorption bands that is obtained in the IR spectrum is definitely going to help us to determine the functional group present in here. In the case of carbonyl, it's going to form a strong signal, but it's also going to give us a sharp signal. In the case of OH present in an alcohol, it's going to give us a strong signal, but it's going to be a broad signal. In the case of OH present in a carboxylic acid, it's going to be even more broad, and that is because of the extent to which it forms the hydrogen bonding. So from here, what we can conclude is, from the nature of the absorption bands, it's possible to differentiate between the functional groups. And finally, not all compounds are infrared active. If you want to analyze a compound by IR spectroscopy, then there should be a change in dipole moment existing in the molecule. Now, let's take a look into these three examples. Obviously, 1-butene can be analyzed by infrared spectroscopy because it is not a symmetrical compound. This carbon-carbon double bond, as it stretches, there is going to be a change in the dipole moment, and therefore an absorption band can be observed for this carbon-carbon double bond. But in the case of 2,3-dimethyl-2-butene, you can see that there is some sort of symmetry in this molecule, and therefore there is not going to be any dipole moment associated with this molecule. So this molecule hasn't got any dipole moment. On the other hand, when you take a look into 2,3-dimethyl-2-heptene, there is going to be only a small difference in the dipole moment, because if you take a look into this, both of these are alkyl groups, and there is only going to be a very small change in the dipole moment. So only a very weak absorption band will be witnessed for this compound. So in order for a compound to be infrared active, there should be change in dipole moment. That is the most important thing. As the bond vibrates, there should be a change in the dipole moment.